Assalamualaikum and good day to everyone and to Dr. Adzrie. And welcome to our presentation on setting up a small-scale electrical power system for a rural village in Tamunan. Our group has been tasked with designing a system that will provide electricity to a common hall in a village in Tamunan. This is my team, which consists of 4 members, including Sagita, myself, Izudin, Ervin, and also Hazik. We understand the importance of providing reliable and sustainable electricity to rural communities, and we were excited to share our design with you today. Our system will be powered by a solar panel array, which will generate electricity during the day. The excess energy will be stored in a battery bank so that it can be used at night or during periods of low sunlight. The power will then be converted to 230 volt of AC using an inverter and distributed throughout the common hall using a wired distribution system. When designing the small-scale electrical power system for the village, one of the first steps we took was to use the Global Solar Atlas to determine the amount of solar irradiance and hours of sunlight that the village receives. We found that Tamunan receives an average of 5.5 hours of sunlight per day, and the solar irradiance is around 5.5 kilowatt hour per meter square per day. This information helped us to design an efficient and reliable solar power system, which will provide a sustainable source of electricity for the common hall in the village. In order to power the common hall, we needed to assess the power requirements for the lights and fans that will be used. The common hall will be used 5 fans and 8 fluorescent lights. These power requirements will be used to design the solar panel array, battery bank, and inverter system to ensure that the system is able to generate and store enough power to meet the needs of the common hall. Additionally, appropriate circuit breakers will be used to distribute the power throughout the common hall and to protect the system from overcurrent and short circuit conditions.
Greetings to Adzrie and my fellow classmates. My name is Ervin Ana Edwin. I'm from 6. Today I'm going to present the implementation of solar PV module in Tamunan, Sabah. What is solar energy? Solar energy is radiant light and heat from the sun that is harnessed using a range of technologies such as solar power to generate electricity, solar thermal energy, and solar. Due to the increase of pollutions around the world, solar energy is one alternative energy source that can maintain life on Earth and environmental friendly. Sunlight, the main source of energy received by Earth, but the intensity is still low due to the Earth's atmosphere and clouds. Although the sunlight is free, but the cost of its collection, conversion, and storage is free. Solar photovoltaic PV module is used to generate electricity from the radiation of solar energy. Now, I'm going to present why solar PV is suitable in Munan, Sabah. Based on the photo that I captured from Google Earth, Tamunan is a valley district under Sabah Interior Division. The valley terrain in Tamunan makes it is a perfect place for paddy crops. Although Sabah is a state where it's windy, but Tamunan does receive more than sufficient amount of sunlight in a year. Here is the climate data for Tamunan from weather-based website. From the data above, Tamunan has high temperature around 30 degrees Celsius to 32 degrees Celsius. Meanwhile, the lowest temperature that was recorded in that district is around 19 degrees Celsius to 20 degrees Celsius. With the storage from the suitable size of battery pack, it is suitable to implement solar PV modules as electric power generation in Tamunan, Sabah. Now, I'm going to present what is solar photovoltaic PV module. The first solar PV module was developed by Bell's Lab in 1904. Solar PV module is used for variety application, making the production improved and cheaper per time. Various materials including silicon, thin film technologies, and new materials such as perovskites are used to produce solar PV module. Solar PV modules are available in a variety of size and configuration to meet a variety of needs and the efficiency and cost effectiveness continue to improve. The solar PV module can be calculated using the formula where open circuit voltage time short circuit current time FF fill factor divided by power input time 100%. Meanwhile, fill factor we can determine it by maximum power voltage time maximum power current divided by open circuit voltage time short circuit current. However, the efficiency of the solar PV module may decrease by time due to lag-induced degradation (LID), cyclic thermal stress, and climatic stress. Meanwhile, the benefits from the implementation of solar PV is clean and green energy, maintenance-free, and of course, reducing electricity bills. Major environmental impact of solar PV module occurs during the manufacturing process, which involves hazardous compounds such as sulfuric acid and hydrochloric acid. Overall, the environmental benefits of solar PV modules are enormous and can considerable outweigh any negative aspects. That's all from my part. Thank you for your attention.
Greeting, I am Adzrie. My name is Mohd bin Muhammad Hassan, and I will present our methodology on sizing the PV system. Designing a whole PV system involves determining a sustainable and cost-effective array size and other components. The PV system size and configuration depend on the appliance, gadgets, and equipment linked to it. Consider each load's power usage and voltage. Lighting and fans use most of the hall's electricity. Assume load energy loss because real-world systems are rarely 100% efficient. We should estimate the 5% load loss, and total electrical appliance is 5799.2 watts. For panel sizing, knowing the sun's peak hour helps size the PV array and inverter. We assume 4.5 hours of peak sun. This design needs 1284.2 watts solar panel. This arrangement requires 7 200-watt solar panels at 12 volts each. Next, designing a PV system requires choosing the right battery size to store additional energy generated by the PV panels during the day for usage at night or during periods of low solar radiation. Battery sizing considers energy demand and discharge depth. The depth of discharge is the percentage of a battery's capacity depleted before charging. Following the equation shown here, total energy required to restore the battery is 944.31 ampere hours. To meet energy needs, 5 parallel connected 200 ampere hours and 12 volt batteries are needed. Moving on to charge controller. Charge controllers regulate power from PV panel to the battery bank in the system. The charge controller must handle the maximum PV array power and battery bank current. Insufficient charge controller can overcharge or undercharge batteries, reducing their lifespan. The charge controller's minimum size is 42 since the PV module short circuit current is 6 ampere and the battery is parallel. The charge controller should be slightly larger than 42 ampere, which is 50 ampere. Next is inverter. Inverter is an important component of a PV system because it converts the direct current, electricity generated by the PV panels, into alternating current. Sizing an inverter can be challenging because some appliances require more power when turning on than their rated power. To ensure the longevity of the inverter and to prepare for future load expansion, it is recommended to consider additional future load expansion when sizing the inverter. In this case, it is assumed that the solar power inverter that will be used is 10,000 watt power with a 12 volt DC input and 230 AC output. Circuit breakers prevent electrical fault and overcurrent in PV system. The circuit breaker size must match the PV array and inverter's power output. The PV array and inverter generate a lot of current, so the circuit breaker must be able to handle it and promptly cut power if there's an overload or short. The current at the PV array and inverter can produce is 25.13 ampere. The circuit breaker rating should be at least maximum current, so the circuit breaker rating must be somewhat higher than the calculated current. Hence, the current rating for the circuit breaker is 31.42 ampere to protect system component. This is for the wire sizing. Proper wire size prevents overheating and fire from exceeding the wire's capacity. Too small wires will shed voltage and reducing system efficiency. The computed circuit breaker size and AWG criteria determine the wire gauge. This system uses 8 gauge wire which can carry 40 amperes. Last but not least, this is the equipment list and project cost estimation.
My name is Sagita Nafada Ramadan, and I will be talking about the operation of the solar power system, which is shown in this block diagram. A photovoltaic solar cell is energized by solar light energy, which the electrical field surrounding the semiconductor layers causes those unbound electrons to move, and this movement results in an electrical current. The charge controller receives this electrical current and use it to energize the battery for later usage. The electricity coming from the charge controller is referred to as direct current, as opposed to the alternating current that powers the majority of households. An inverter can quickly convert DC into AC electricity. After being transformed from DC to AC electricity, the solar energy is then dispersed throughout the house to power your appliances. The additional safety measures that are being considered are circuit breaker, fire extinguisher, and electrical room. As we know that electrical overloads can produce high heat, which could lead to sparks, burns, electrocutions, and fires. A circuit breaker can instantly stop the flow of current. A fire extinguisher that is recommended is the carbon dioxide extinguisher, which works by displacing oxygen or taking away the oxygen element of the fire triangle. CO2s are designed for Class B and Class C, which are flammable liquid and electrical fires only. And the electrical room is a room or area designed for housing all the delicate electrical equipment which are needed for communication or power distribution in a facility. They provide sensitive, potentially hazardous electrical equipment with safe, convenient storage. Thus, it makes maintenance and operation significantly safer and more convenient. That's it from me. Thank you.
In conclusion, our team has successfully designed and installed a small-scale electrical power system for the rural village of Tambunan. By utilizing a solar power system, we were able to provide a very reliable and renewable source of electricity to the common hall that give power to the lights and fans for the villages. This project not only improves the quality of life for the villagers, but also serves as a model for the rural village community that looking to improve their access to electricity. And throughout the project, we faced several challenges, but we were able to overcome them through a collaborative effort between our team and the village community. And finally, we look forward to possibility of expanding the system to serve more villages in the future. And we also encourage the village community to take ownership of the system and teach them on how to maintain it throughout the time. On behalf of our team, I would like to thank you for all the attention given. That's all from us.